Hey everyone, Mr. Chapter here to take a look at antiderivatives, our first exposure to antiderivatives, and learn how they can help us work backwards. First, understand that functions with the same derivative differ by a constant. Suppose f prime of x equals g prime of x at each point of an interval I. And there's some constant c such that f of x equals g of x plus c for all x in I. For example, if you have some function, and we'll call it f prime because we're going to assume it's a derivative. So suppose that f prime of x is equal to 2x. Then there are a lot of functions that could have originated from this to give us a derivative 2x, right? So let me give you one, we'll call it f. f of x is x squared. Right? The derivative of x squared is 2x. But g of x could have been x squared plus 2, right? The derivative of x squared plus 2 is 2x. And h of x could have been x squared plus 3, right? There are a whole family of functions that could have been equal to this derivative. And so what we say is that the actual antiderivative is x squared plus c, where c could be any constant. So this is the antiderivative when you're working backwards. We usually notate an antiderivative with a capital f of x, meaning that we worked backwards. And that's exactly what the antiderivative definition states. So a function capital F of x is an antiderivative of a function lowercase f of x if the derivative of the antiderivative, so this is a lot of notation in one, the derivative of the antiderivative, right, because capital F is antiderivative, prime means I differentiated it, is equal to f of x, lowercase f of x, for all x in the domain of f. The process of finding an antiderivative is known as antidifferentiation. You're basically working backwards. Think of it like this. Suppose I give you velocity and I ask you for position. Okay? Before, a particle motion problem states that a particle moves along the x-axis, so its acceleration at any time t is given by a of t equals 6t minus 18. Antidifferentiation is really easy in terms of particle motion because we all know that position is like the beginning, and then the derivative of that is velocity, and then the derivative of that is acceleration. So I know the antiderivative of acceleration is velocity, and the antiderivative of velocity is position. So it basically works in reverse. It's kind of a nice visual way to see antidifferentiation. At time t equals 0, the velocity of the particle is v of 0 equals 24. This is needed because we just said that you could have an infinite number of antiderivatives, a whole family of them, but there's only one that will satisfy that initial condition. Also, an initial condition of position is given that x of 1 has to be 20. So the first part of the problem says write an expression for velocity of the particle at any time t. So if I were to start with that, I know that the acceleration was given to me as 6t minus 18. So my velocity is basically going to be the function that I take the derivative of to get the acceleration. So the question is, what could I take the derivative of to get 6t as an answer? Well, I know it has to be quadratic because I know that the derivative of anything quadratic will bring me down to a linear. So the question is, what value do I put here in order to get 6t? Well, it has to be a 3 because the power rule, the 2 comes down and multiplies with that number, so that number has to be a 3. You all agree the derivative of 3t squared is equal to 6t. Same thing goes, what would I take the derivative of to get negative 18 as an answer? Well, negative 18t, of course. However, I would need to do plus c, because there's any constant that could go there, 1, 2, 3, 4, 5. If I took the derivative of any of those, they would be 0 and go away. This is when the initial condition comes into play, that v of 0 must be 24. So I plug v of 0, I plug 0 into t, I plug 24 into velocity, and I solve for c. So 24 equals 3 times 0 squared minus 18 times 0 plus c, so c is 24. That tells me that the velocity function that I want is 3t squared minus 18t plus 24. This is the only one that has the acceleration function given and satisfies the coordinate of v of 0 equals 24. Part B. For what values of t is the particle at rest? Well, remember back in the day we learned that a particle is at rest when its velocity is equal to 0. So if I were to do that here, I were to set 3t squared minus 18t plus 24. If I were to set that equal to 0, I could factor out a 3, and that would be t squared minus 6t plus 8 is equal to 0. And then I could factor this, so that would be what? T, it's got to add up to 8, so it's got to be double negative, so I'm thinking minus 4 minus 2 equals to 0, which tells me that t is 4 and t is 2. So at t equals 4 and t equals 2, the particle is at rest. Next question. Write the expression for x of t of the particle for any time t. Okay, well, again, I know my velocity function, so I'm going to write that right here. Velocity is equal to 3t squared minus 18t plus 24. And I know my position is basically the reverse of that. So position, I take the derivative of something, and I get 3t squared as the answer. Well, it has to be t cubed. The derivative of t cubed gives me 3t squared. And the derivative of the derivative of something that gives me negative 18t should be negative 9t squared. Take the derivative of negative 9t squared, and I get negative 18t. And then, of course, the derivative of what would give me 24, and that would be 24t, plus some constant c, because the derivative of any constant is 0. I go up, I look at my initial condition. My initial condition is x of 1 equals 20. So that's what I need to use right here. So I plug 20 in for position, and I make t be 1. I solve for c, which would be 4. So that tells me the position is equal to t cubed minus 9t squared plus 24t plus 4. This is the only position function that has the acceleration provided and the initial condition of x of 1 equals 20. Part D. Part D asks, find the total distance from 1 to 3. Okay, from 1 to 3. So that means I need to consider the turnaround points. Are there any turnaround points between 1 and 3? Yeah, 2. So I know it turns around at 2. So I need to find the distance. I need to find the distance from 1 to 2, and then from 2 to 3, right? Which means I need to find the position at 1, the position at 2, and the position at 3. And then if I find these, I can find the total distance. Well, the position at 1, I believe, was given to us as 20. That was the initial condition, interestingly enough. I don't even have to do the math out. X of 2, I'm going to have to go find. So I need to plug a 2 into the position. So that would be 2 cubed minus 9 times 2 squared plus 24 times 2, and then plus 4. And that would give me 24. And then if I plug a 3 in, so 3 cubed minus 9 times 3 squared plus 24 times 3 plus 4, and that would give me 22. So let's consider the distance. So the distance from 1 to 2, particle starts at 20, particle moves to 24. That's a total of 4 distance, or 4 meters, or whatever I'm measuring this in. Then, particle starts this time right here at 24. Particle goes to 22. That is a total distance of 2 meters or feet or whatever. That means that the total distance, the distance on 1 to 3 is equal to 4 plus 2, which is equal to 6. I don't know, is it meters? I'll look back up. Look back up, look back up, look back up, and no, nothing provided, so we'll just call it meters. So the distance on 1 to 3 is 6 meters. So this is your first introduction to an antiderivative, working backwards.